Okay, we're going to be starting the new unit today, and it's all about stoichiometry. We've done some stoichiometry in the past. We did compositional stoichiometry, where we use the relative amounts of a particular element in a substance. So, for instance, H2O, we'd have 2 atoms of hydrogen for 1 molecule of water. Uh, that was back in the CPM unit that we did, counting particles by mass. Well, now we're going to be doing reaction stoichiometry. And the problem with most presentations of stoichiometry is that it does not provide a sense of the changes that are taking place in the chemical reaction. So we have taken the time to write balanced chemical equations, talked about how the reactants break apart and then reform into the products. Well, in stoichiometry, we're going to be calculating the amounts of the reactants that are reacting and the amounts of products that end up forming. Most methods use a plug and chug method of predicting the amount of products and reactants, but does not provide the opportunity to see how much of the reactant was used and how much product is forming. So we don't do the typical just straight up dimensional analysis version of stoichiometry. We use in my opinion, a much better method. And it's through the use of something called BCA tables, which we'll get to in a minute. The method that we will use involves writing a balanced chemical equation using coefficients to relate amounts of one substance to another, and then using ratios to convert between units, whether that be mass to moles, moles to mass, or moles to moles of a substance. Stoichiometry is the process of determining how much product is made or how much reactant is needed during a chemical reaction. As we know, in a chemical reaction, atoms are conserved. So the total mass must be conserved, and we show that with a balanced chemical equation. Balanced chemical equation tells us 2 things: what we begin with and what we end up with, and then also the ratio of particles involved. This ratio can be seen either as a ratio of individual particles or as a ratio of moles. Remember back in the CPM unit that there are 6.022 times 10 to the 23rd particles in 1 mole of a substance. Well, chemistry does take place between individual atoms or molecules at the atomic level, but for us in the lab, when we measure things out, we're going to be measuring mass of things, and that means we're going to be dealing with lots and lots and lots of atoms, particles, moles. So we use moles in talking about reaction stoichiometry. So as it says here in the lab, it's only practical to work with moles rather than the individual pieces. So we interpret our equation as a ratio of moles. So here we have a balanced reaction equation for the burning of magnesium metal to make magnesium oxide. And instead of reading it as 2 atoms of magnesium and 1 oxygen molecule making 2 units of magnesium oxide, we replace that with moles. So for every 2 moles of magnesium burned, 1 mole of O2 is required. So in other words, if we have 12 times 10 to the 23rd particles of magnesium, we need to have 6 times 10 to the 23rd molecules of oxygen. So a 2-to-1 ratio. So we use moles instead of talking about the atoms or the individual molecules. So we have these various ratios, and we can use this mole ratio relationship. You can hear me talk about mole ratios a lot today, to make predictions about how much we need of something or how much we can make from what we have. Being able to take the balanced chemical equation and write these mole ratios is an important part of this process. So we'll be using them as conversion factors. If we know an amount of one substance, we can convert to an amount of another substance by using these mole ratios. So in this first example here, I have my mole ratio of magnesium to oxygen. This 2 for the 2 moles of magnesium comes right from the balanced chemical equation, and the 1 for the 1 mole of oxygen also comes from the balanced chemical equation. So we could say we have 2 moles of magnesium for 1 mole of oxygen, or we could flip it like you can with any conversion factor and say that there's 1 mole of oxygen for 2 moles of magnesium. If we were to write out all of the mole ratios, this is what we would end up with. So the ratio of oxygen to magnesium oxide and the ratio of magnesium to magnesium oxide. So we can relate reactants to reactants or reactants to products. And notice this note here at the end here. It says don't simplify the mole ratios. This last one, we have 2 moles magnesium or 2 moles of magnesium oxide. It might be tempting to simplify and say it's really a 1-to-1 relationship. Don't simplify the ratios. Okay, just leave them be. I've seen too many times where people go to simplify things, they end up writing down the wrong number and end up messing up their calculation. So as far as the stoichiometry process on its own, in every reaction there are 3 stages to consider to make good predictions, and that is before, change, and after. The before is what we have before the reaction takes place. Change is how much of each substance actually changes during the reaction, so how much reactant is used, how much product is produced. And then after, how much of each substance is present after the reaction is complete. Good organization can help us make good predictions. Therefore, we have an organizational table that can help us track the before, change, and after for reaction. So here's our first example. Hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. How many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? Step 1 of the process is to write a balanced chemical equation. So we have hydrogen sulfide burning in air makes sulfur dioxide and water. And so here we have our balanced chemical equation. 2H2S plus 3O2 yields 2SO2 and 2H2O. And then below it, we have listed the before, the change, and the after, which we'll be filling in as we go forward. Okay. It's very important in this process that we start with the correct balanced chemical equation, because if it's not correct, then the whole problem is going to calculate out wrong. Step 2, after the balanced equation, is to fill in the before line with the given information. Mark what you must find on the table with units. Assume reactants you don't have amounts for present with more than enough available is in excess. Okay, if you go back and read the question, it only tells us that we're starting with 2.4 moles of H2S. And so I've put that number into my table, and it doesn't say anything about the oxygen. Well, this reaction won't work if there's not oxygen present, so therefore we assume that we have an excess amount of oxygen, plenty of oxygen. And since it's before the reaction has started, we have 0 sulfur dioxide and water. The other thing that's really important with this is that in the BCA table, we only put moles in a BCA table. Never mass. We're going to see a question in the examples later where we're going to start with a mass value. A BCA table only ever gets moles of substance put into it. Okay, so if I had started with a mass of hydrogen sulfide, I would have had to have converted that to moles, and we've done that in the past. Mass divided by the molar mass of the substance gives us the moles. Now for step number 3, it says use ratio of coefficients to determine the change made. Well, that's the mole ratios. And so in the question, it says we start with 2.4 moles of hydrogen sulfide, and I need to figure out the amount of oxygen that's going to be used, and so I need the mole ratio between oxygen and hydrogen sulfide. And using that, 2.4 times 3 moles of O2 divided by 2 moles of H2S leaves me with 3.2 moles of oxygen. And so I can bring that down and fill in that information. So I'm going to be using up all of my hydrogen sulfide, and I put a negative sign because I'm using it up, so I should have less after the reaction. I've now calculated the amount of oxygen gas that is required, so I have that in there. And then I've got this blank on the other side because now that the reaction is taking place, I'm going to be forming those products. So I would also need to calculate those. But if you notice in the reaction equation, there are 2 moles of hydrogen sulfide in the reaction equation, and then on the product side we have 2 moles of sulfur dioxide and 2 moles of H2O. So if two substances have the same coefficient, then they'll be consumed or produced at the same rate. And so we don't need to use the mole ratio to figure that out, since there's already 2.4 moles of hydrogen sulfide going to be being used up. If there's 2 moles of H2S in the reaction, 2 moles of sulfur dioxide, then I know that I'm going to be making an equal amount of sulfur dioxide and also an equal amount of water. So as long as you have matching coefficients, you can match up the change values in your BCA table. For step 4, complete the table for what remains after the reaction. Well, this is just a process of doing the math. 2.4 minus 2.4 leaves you with 0 moles of hydrogen sulfide. So that is all used up. It is gone, and the reaction is going to stop. Since we began with an excess amount of oxygen and we use up 3.6, we can't get an exact value, so we just say that there's oxygen still remaining. And then since we started with 0 products and we made 2.4 moles of each, then my after line shows that I have 2.4 moles of sulfur dioxide and water present. And so my final answer, since I want to know how many moles of oxygen gas are needed, 3.6 moles of O2 are needed to burn 2.4 moles of hydrogen sulfide. If the question had asked us for the mass of oxygen gas required, then we'd have to do that extra step and convert moles to mass by using the molar mass. And so we have 3.6 moles of oxygen times 32 grams for 1 mole of oxygen gas. We have 115 grams, and so in that case the answer would have been 115 grams of oxygen gas are needed to burn 2.4 moles of hydrogen sulfide. We're going to run through 3 more examples that you can use. Again, I'm going through these pretty quickly, so if you need to pause the video, make sure you do so. So here it says lead will react with hydrochloric acid to produce lead chloride. It's supposed to be lead 2 chloride. And hydrogen gas. How many moles of hydrochloric acid are needed to completely react with 4 moles of lead? So step 1, balanced chemical equation. 1 Pb plus 2 HCl yields 1 PbCl2 and 1 H2. Step 2 is to fill in the before line. We're starting with moles of lead, so we can just put in the 4.0. And then we have an excess of HCl because we don't know how much we're starting with, and then 0 for our products. And then we get to the change line. We're going to be using up all of the lead because that's the only thing we know to start with. But I already know that because I have 1 Pb and 1 PbCl2 and 1 H2, those matching coefficients, I know that my change for the lead 2 chloride is going to be 4 moles and the change for the hydrogen gas is going to be 4 moles. Question is, and I have a box here, what is going to be the change for the hydrochloric acid? Well, we know we got 4 moles of lead, and then I'm going to use my mole ratio of hydrochloric acid to lead, which is 2 moles over 1 mole, and that will yield me 8.0 moles of HCl. So in this reaction, use up 4 moles of lead, use up 8 moles of HCl. I can then fill in my after line. It's going to leave me with 0, excess, 4 moles of lead 2 chloride, and 4 moles of hydrogen gas. So now I can answer the question. The question wanted to know how many moles of hydrochloric acid are needed to completely react. And the answer is 8 moles of HCl is required to react the 4.0 moles of lead. Example number 2. How many moles of hydrogen gas will be produced if 2.5 moles of calcium hydride react according to the following equation? Well, we've got the balanced chemical equation already, so we can go right to step one, or excuse me, right to step two. Fill in what we know. We know we're starting with 2.5 moles of calcium hydride. Doesn't say anything about our other reactant, which is water, so we'll put that in excess. And once again, we're starting with no products. For my change line, I'm going to be using up all of my calcium hydride. And because that's in a 1-to-1 ratio with the calcium hydroxide, I have that filled in already. But now I'm going to need to calculate my other mole values, the amount of water that's being used or the amount of hydrogen gas that's being produced. Notice that the ratio of calcium hydride to water is going to be 2-to-1, and it would also be 2-to-1 with hydrogen to the calcium hydride. So really we just need to find one of those values. And so I set up my calculation here. 2.5 moles of calcium hydride times my mole ratio. 2 moles of H2O over 1 mole of CaH2. Remember, the 2 and the 1 in my mole ratio come from my balanced chemical equation. That means I'm going to be using up 5 moles of water in the reaction, but that also means I'm going to be producing 5 moles of hydrogen gas on the other side. And then I can do my after line. 0 excess, I made 2.5 moles of calcium hydroxide and 5.0 moles of hydrogen gas. Which takes us to the last bit then. What's the answer to the question? Well, they want to know how many moles of hydrogen gas would be produced, and according to our BCA table, 5 moles of H2 will be produced by reacting 2.5 moles of calcium hydride with water. The final question says, how many moles of water will be produced if 8.5 grams of oxygen reacts according to the following equation? What mass of water would be produced? So here's something a little bit more in line with what we would find in the lab. We don't measure moles in the lab, we measure things by mass. And so step one, balanced chemical equation, but then before we can start filling things into the table, we are going to need to convert that 8.5 grams of oxygen to moles of oxygen. So in that first step, here we have our 8.5 grams of water times the inverse of the molar mass of H2O, which is about 18 grams. That's 2 hydrogens at 1 gram per mole each, plus 1 oxygen at 16 grams per mole, which gives us the 18. And we end up with 0.47 moles of H2O. And so that is our initial value of oxygen. The C6H6 is in excess. The other ones are 0 because they haven't been produced yet. Now, because of this reaction here, you might notice all the coefficients are different. So we're going to have to do 3 separate calculations in order to finish our change line. So we know we'll use up all of the oxygen gas. Excuse me. But we're going to need to do 3 separate calculations to get the rest of the change line. And so that's what we have here. We're starting with the 0.47 moles of oxygen times our mole ratio to C6H6, which is 2 moles over 15 moles of O2, and that equals 0.063 moles of C6H6. And then I've got my ditto marks here because we're starting with the same mole of oxygen, but I got my new mole ratio, 12 moles CO2 over 15 moles of O2, and then the last one, 6 moles of H2O or 15 moles of O2, and you can see the values that we end up with there. Once we have those, we can plug those numbers into our table. So negative 0.063, we're going to be going up by 0.38 moles and up by 0.19 moles. Now I can do the afterline. We're going to have an excess there because that's what we started with. No oxygen gas left over. We will have made 0.38 moles of CO2 and also made 0.19 moles of water. Now, the question wants to know how many moles of water will be produced. Well, we've got that answer right now, 0.19 moles of water. But it also asks what mass of water is being produced. So scroll back down. To get the mass of water, we know how many moles of water, and so this time we multiply by the molar mass, and it works out to be 3.4 grams of water. And so our final answer is 0.19 moles or 3.4 grams of water are produced by reacting 8.5 grams of oxygen with C6H6. Okay, that's everything that I have for you. If you need to go back, rewatch some things, hopefully you were pausing along the way so that you could stay caught up with everything. But use those notes as your examples while you work on Stoichiometry Worksheet 1. You need to show all of your work just like I did in the questions here, and that assignment is due on Monday.